I want you to imagine something. Picture a titan of steel and silicon, a multi-million-dollar machine, right? It's powerful enough to lift a car with just the flick of a wrist. But right now, it's completely, utterly useless. It's just sitting there in a silent room, a helpless giant. And you have to ask, why? Well, it's simple. It's blind.
Now, seriously, just think about that for a second. What good is all that power, all that precision? What's the point if it can't even see the hand in front of its own face? Absolutely nothing. That's the stark reality of it. You see, without the gift of sight, a robot is just, well, it's a glorified wind-up toy. It's trapped in this endless loop, repeating the same exact motion over and over and over again. Forever. There's no freedom, no intelligence. It's just trapped.
So the big question is, how do we break it out of that prison? Well, we're going to give it the gift of sight. Today, we're about to embark on this incredible journey into what's called robotic perception. It's like alchemy, really. It's the process that turns a blind machine into an intelligent agent that can finally see and actually understand our world.
And this is our treasure map. It charts the entire incredible journey we're about to take. It starts with a single photon of light hitting a camera lens, and it goes all the way to what is essentially a conscious decision inside the robot's mind. We're going to keep coming back to this map as we uncover each and every piece of the puzzle, one by one.
Okay, so our journey begins right here. And yeah, not very glamorous, is it? What you're looking at is the robot's very first, totally unfiltered glimpse of the world. It's just this chaotic stream of pixels coming from a simple camera. This raw data, it flows into what you can think of as the robot's central nervous system, which is a framework called ROS2. It's all happening on a data channel that's just called /image_raw. But here's the thing. A stream of pixels is just noise, right? It's the huge difference between simply looking at something and truly seeing it. The robot has all this data, but it doesn't mean anything yet. So the real question is, how on earth do we teach a machine to understand what it's looking at? Well, for a job like that, you need a real powerhouse. And that is where OpenCV comes in. Just think of this as the robot's visual cortex, the part of the brain that actually processes sight. It's this massive open-source library packed with digital tools all designed for one single purpose: to take that chaos of raw pixels and find the meaning that's hidden inside.
So how does the computer actually, think about an image? It's kind of fascinating. It doesn't see a desk or a chair like we do. It just sees a problem that needs to be simplified. So the first thing it does, it throws away all the color, just converts everything to grayscale. Then it blurs the whole image, kind of like when you squint your eyes to just see the main shapes. Next, it cranks up the contrast until everything is just pure black and white. It's only after all of that that it can finally start to trace the outlines, the contours of the objects in the room.
And check this out. This is the incredible result. Just look at that difference. It's a total transformation, right? It goes from a messy, confusing scene into this clean, super understandable map of shapes and outlines. The robot is literally making the invisible visible.
Okay, so this is a huge step forward. The robot can now identify shapes in a flat, two-dimensional image. But there's a big problem. Our world isn't flat, is it? So how do we get the robot to, break through the screen and start understanding our actual three-dimensional reality? All right, the core of the problem is really this. A camera sees the world in what we call pixel space. It's like you're looking at a photograph. It's just a grid of dots, and there's no sense of real-world scale at all. But the robot, it needs to live in image space. It needs to know that, say, 200 pixels equals exactly 1 meter in the real world. Basically, it needs a ruler, not just a pretty picture. And you're not going to believe what the key to solving this massive problem is? It's this: a simple chessboard. Seriously. By showing the camera a pattern where we know the exact real-world size of those squares, we can perform something called a calibration. This whole process is kind of like giving the camera a new pair of glasses. It corrects for any distortion from the lens, and it creates that absolutely crucial mathematical map from flat pixels to physical reality. Okay, so now our robot can identify an object. It can even measure its height and width. That's awesome, but there's still a huge critical blind spot. Think about it. It knows what an object is, but it has absolutely no idea where it is. Is that thing an inch from its face, or is it a mile away? The robot has no clue.
So yeah, it's time to solve that problem once and for all. It's time to give our robot true depth perception, and finally bring it out of that flat world and into our rich, three-dimensional universe.
And the answer is a whole new kind of eye, a depth sensor. This little device here, an Intel RealSense, works a bit like a bat sonar, if you can believe it. It's actively measuring the distance to every single pixel it sees, and it uses that info to create a 3D map of the world in real time. For all you nerds out there, that map is technically known as a disparity matrix.
Now, having all this new 3D data is fantastic, but it's like learning a completely different language than a 2D image. So, just like we needed OpenCV for the 2D stuff, we now need a new tool for 3D. And that tool is the Point Cloud Library, or PCL. The easiest way to think about it, it's literally the OpenCV for 3D. It's designed specifically to handle these enormous point clouds. We're talking millions of individual docs that map out the entire world in 3 dimensions.
And just look at this right here. This is the massive leap in understanding. On the left, you've got the normal color image. That's what the robot sees. But on the right, you have the depth image, and that's what the robot knows. It's a huge difference. It's not just about colors anymore. This is a measurable 3D map of the physical world. So, we've done it. A robot can see in 3D. Amazing. But of course, this creates one final, massive hurdle. I mean, we are talking about millions upon millions of data points being generated 30 times every single second. It's a digital tsunami of information. So the question becomes, how could any normal computer possibly keep up with that?
Well, a standard CPU, the main brain of a computer, it's kind of like a single, really fast cashier. It handles one task at a time, and it does it very well. But when you hit it with this flood of data, it just creates a massive bottleneck. The solution? It's the GPU, the graphics processing unit. A GPU isn't one cashier. It's like opening 1,000 checkout lanes all at once. It's built for doing tons of things in parallel, which is exactly what you need for this kind of perception work.
And this is where a really specialized toolset comes into play. NVIDIA's Isaac ROS. You could think of these as robotics packages that are built from the ground up to speak the GPU's native language. They're smart. They keep the data on the GPU as much as possible, so you're not wasting time sending it back and forth to the CPU. And the result? Truly mind-boggling speed.
And this is what that speed actually looks like in the real world. That robot can instantly, and I mean instantly, spot those black and white markers and know their exact 6D pose. And that doesn't just mean their position, it means their precise orientation in 3D space. We're not just talking fast here. This is real-time, superhuman sight. It's the kind of thing you absolutely need for warehouses, for self-driving cars, and, well, for the future.
So let's go back to our map one last time. We started with just a raw camera feed, then we decoded the image with OpenCV. We grounded it in reality with calibration. We added that crucial third dimension with a depth sensor, and finally, we're processing it all at light speed with NVIDIA Isaac. From a single lonely pixel all the way to full 3D perception. The journey is complete.
So, we've built a machine and given it the gift of sight. But let's be real, all of this has been in a perfect, controlled lab. What happens when we take it out into the real world? What happens in the dark? In the rain? What happens when things move too fast to track? What happens when this perfect system is pushed to its absolute breaking point? Well, that's a story for next time. Hari har!